This is an example of rotational dynamics, of conservation of momentum. So we have here a uniform rod that's horizontal. The axle is vertical and there's no friction in this axle. The system is at rest right now. The rod is at rest. And the rod has some characteristics, 2.6 kilograms, total length of 80 centimeters. We're firing a bullet that has a mass of 3 grams, and this bullet has a speed of 290 meters per second. So it's going to impact the rod, and it's going to be captured by the rod. It's not going to pass on through. We're going to say it strikes a rod and is captured. And it strikes a rod 30 centimeters from the axle. So it's not out at the end. It's 30 centimeters away from the axle. We want to know what's the angular velocity of the system after the bullet impacts the rod. Well, this system is set up for conservation of momentum. Conservation of energy will not work because we have an inelastic collision. The bullet is being captured by the rod. So we use conservation of angular momentum. The rotational inertia I1 and omega 1, that's at the start of the problem, equals rotational inertia times omega 2, the angular velocity after the impact occurs. You might ask yourself, is the angular momentum zero? At the instant before the bullet hits the rod, is the angular momentum zero? And the answer is no. The rod is not rotating. Its initial angular velocity is zero. But the bullet has a linear momentum at a certain distance away from the axle. So it does have mvr of angular momentum, and this whole quantity here, I omega, is angular momentum. I'll abbreviate. So the I omega is angular momentum, and for the case of the bullet, at the time when it's just impacting the rod, its angular momentum is mvr, mass of the bullet, velocity of the bullet, and the distance to the axle. So after, when we consider the system afterwards, the moment of inertia is in two parts. There's a moment of inertia of the rod and a moment of inertia of the bullet. If you'd look in a table for formulas of moments of inertia, you would find that we have 1/12. I'm going to use capital M and then L squared, M being the mass of the rod. So I'll put bullet here, rod here, and then the omega that we have afterwards. The omega of the rod is 0 to start with, so just have the omega symbol on the right side. So that's the rod, and then we have the bullet. The situation for the bullet when it's embedded in the rod and it's now going to move in a circle. This is a point mass, so its I value is mr squared, rotational inertia value, moment of inertia value, mr squared. And we have the same omega for the bullet as we do for the rod. The linear velocity varies along the rod location, but everything's moving with the same angular velocity. So these omegas are, in fact, the same. So let's go ahead and put some numbers in here. So we have, I'll slide the page up just a little bit. The mass of the bullet is 3 grams. We need to use kilograms. We need to use standard metric units. So 3 times 10 to the minus 3 kilograms, 290 for our speed in meters per second, and 0.3 is how far out from the axle we impact the rod. And then 1/2, the mass of the rod is 2.6 kilograms. And the length of the rod is 80 centimeters. Again, need to use standard metric units, 0.8 meters, and we'll square that. And omega is what we're trying to find. Then again, the bullet, so 3 times 10 to the minus 3, and 0.3 squared, and omega. So this is our conservation of momentum expression. And simplifying this a little bit, we can multiply the numbers here on the left side, and you should verify my numbers. I got 0.261. Here for the rotational inertia of the rod, I've got 0.1387. And for the rotational inertia of the bullet, mr squared, just a single point mass we're treating this as, I've got 0.00027. Almost went to scientific notation with that, but I think I have the number of zeros copied correctly. Well, we've got like terms here, so we add those up and divide into 0.261. If I have done this properly, and I'm going to just go ahead and add these up here. 0, 0, 0, nothing happening there, and 0.13897 omega. The 2 is in the position of the 7 here, so I think I've added those correctly. Again, you should check this, check my work. Now I'm ready to divide and find omega, and the omega I come up with is 1.878 radians per second, or roughly 1.88 radians per second. So there's our omega using conservation of momentum. What about the kinetic energy of the system? How is that conserved or not conserved? Or we have the ability to calculate it. So before, the rod is not moving, so all the kinetic energy is in the bullet, mass of the bullet and its speed squared. So 1/2, the mass of the bullet is 3 × 10⁻³ kilograms, and its speed is 290 meters per second. We have to square that. And again, you should check my calculations, but I came up with roughly 126 joules. 126 joules of kinetic energy in the bullet. After the impact, all the kinetic energy is in rotational form. So 1/2 I rod omega squared plus 1/2 I bullet omega squared. And we know the I values, we've worked them out up above, so 1/2, and we have 0.1387 for the moment of inertia of the rod. And we have the omega 1.878, we'll square that. And for the bullet, its moment of inertia, 0.00027, and again 1.878 squared. So rotational kinetic energy is 1/2 I omega squared. Some of it's in the rod, some of it's in the bullet. And if we complete the calculation here, there's really we can factor off the 1/2 and the 1.878, and then multiply by 0.13897, adding these two i's together again, as was done above. But any way you do it, go ahead and do it. And I came up with the kinetic energy after this collision, kinetic energy after the collision, of 0.245 joules. This is definitely inelastic. We've lost kinetic energy. Kinetic energy is not conserved. With the bullet, we had 126 joules of kinetic energy. With the rotating system, 0.245 joules of kinetic energy. So if you have questions, please ask your instructor.